Okay, welcome back everyone. In this next segment, and the last one for this unit, we're going to talk about what happens when an RC circuit is discharging. So in the previous lesson, we talked about how RC circuits charge up, that basically a battery is going to cause current to flow. But now, when we discharge a capacitor, we're going to disconnect the battery and the capacitor is going to drain. Because there's no more electric potential difference from the battery, there's no reason for the charge to stay on the capacitor. And as a matter of fact, it's at a higher voltage on the capacitor when we first disconnect it, and that voltage is going to decrease as the electrons get to a lower energy. So here it is. Initially, the capacitor is charged to a value Q naught, and we're going to be using that. I is 0, current has ceased, and we close the switch. So what's going to happen is that both the current and the charge will decrease over time. Okay, but what we're going to notice is that we're going to have a negative current versus time for the discharging capacitor, and this is because its direction is opposite what we had previous. Instead of the capacitor filling up, now charge is leaving it. And then here's the charge versus time on the capacitor. And again, we're going to start at this value Q naught, which we'll use in our calculations. Okay, so the time constant is still tau, and it increases with resistance for the same reason as before, that larger resistors decrease the current, and this means that less charge per unit time is leaving the capacitor, so it takes more time to drain. Likewise, it increases as capacitance increases, because if we have a larger capacitor, there's more capacity, and it takes longer to drain. So here's our look at what the RC constant does for us. After a time equal to RC, our charge has decreased to a factor of Q naught over E. And so after one time constant, we have about 64% less of our original charge. Okay, so we only have about 36% left. And the current is also dropping by 64%. So that's the value basically of 1 over E is about 0.36. Okay, so the voltage on the resistor is still IR, which is dq dt. The voltage on the capacitor is still Q over C. So now our differential equation is IR plus Q over C equals 0. And now we have replaced our negative signs with positive signs because the current is in the opposite direction. So this is another differential equation involving charge. And really all we need to do to solve this is take the dq dt R term and bring it to the other side. So we're going to solve this in OneNote. So flip over to this. And so remember that what we had was IR plus Q over C is equal to 0. And we said that we would take IR and bring it to the other side. So we have Q over C is equal to negative R dq dt. Let's separate these variables. And right away, you're going to see that we have negative 1 over RC dt is going to be 1 over Q dq. So the math for discharging is a little bit simpler because we don't have the EMF or the voltage from the battery to worry about. So then what we do is we just integrate. And this side will be from 0 to t of negative 1 over RC dt prime. And now we have to be careful because we still have 1 over Q dq. But now let's think about the limits. Are we starting with 0 charge on the capacitor? Well, the answer is no. We're starting with Q naught. And if you put a 0 there, then the math is not going to work out, as you'll see in a second. And we're going to go from 0 to some later charge q, which is what we want to solve for. So the left side is easy, negative t over rc, and the right side is not too terrible. It's just going to be the natural log of q prime evaluated from q naught to q. Now you see why this can't be 0, because if it was, we would have an undefined value. Can't take the natural log of 0. Okay, so the math sort of keeps the physics in check, if you will. Alright, so negative t over rc is equal to the natural log of q over q naught. Remember, q naught is what we start with on the capacitor. We exponentiate each side, and we get a very simple expression that q over q naught is e to the minus t over rc. So we just multiply by q naught on each side, and we get our expression for q as a function of time. And that matches very nicely with what we wrote, that if this is q naught and q as a function of time, that it would decrease exponentially. And at rc, you'd have basically q naught over e. Okay? Because if you think about it, when t is equal to rc, we didn't do this in the last video, but just check this out. When t is equal to rc, q is equal to q naught times e to the minus 1, which is just q naught over e. So that's how we know that we have 36% of the original charge. And finally, we can calculate an expression for, or derive an expression for the current, because I is just dq dt, and so that's just going to be negative 1 over rc times q naught e to the minus t over rc. And you might recognize that q naught over rc is actually I naught. Well, how do we get that? By recognizing that q naught over c is the voltage on the capacitor, and that voltage divided by resistance will give us the initial current. So I is actually equal to negative I naught e to negative t over rc. Okay? And so that is going to be another exponential decay, but starting with a negative value. Okay, so if this is current and time, again we can mark RC on here, and we get I naught over E after a time constant of RC. Okay, so back to our PowerPoint here. All right, and so that's what our diagram looked like of the circuit. And we do have some boundary conditions. Okay, we know that Q of t on the capacitor is equal to Q max, or also Q naught, at t equals 0. And basically, the current is going to be equal to 0 at t equals infinity. And so the capacitor is going to be empty at t equals infinity, and both the charge and the current will tend to 0. And we saw that in the graph. Okay, so here was our general solution. Q of t is Q naught e to the minus t over RC, and I is equal to I naught e to the minus t over RC. Should be a negative sign there, showing that it's in the negative direction. Okay, and so everything works out here because when t is 0, Q is equal to Q max. And you can also see that as t goes to infinity, that both charge and current go to 0. So all of that checks out. Okay, so both charge and current decrease over time. All right, so here's an example. Okay, so we have the same circuit as before, where we have our 10 mega ohm resistor connected in series with a 1 microfarad capacitor. So remember, that means that our time constant is equal to RC, which from the previous video is 10 seconds. And we have a battery with an EMF of 12 volts that's disconnected. which turns out to be irrelevant because we don't have a battery when it's discharging. So we want to assume that when t is equal to 0, Q naught is equal to 5 microcoulombs. So that's Q naught. And what we want to do is we want to calculate when is the charge equal to 0.5 microcoulombs. And also, what's the current at that time? So we can set up our equation that Q is equal to Q naught e to the minus t over RC. And we're going to have to solve backwards. This will be 0.5 microcoulombs. This will be 5 microcoulombs. And it'll be negative t over 10. Okay? So basically, that's going to be 1/10. 1/10 is equal to e to the minus t over 10. And in order to get rid of that e, we're going to take the natural log of each side. So I'll bring that up here because we have a lot more work to do with the current. So that means that the natural log of 1/10 is equal to negative t over 10, which means negative t is equal to 10 natural log of 1/10. And one nice property of logs is that we can flip the fraction if we stick a negative sign in front of it. So t is just equal to 10 times a positive log of 10, and that comes out to be approximately 23 seconds, about 23.03, but we're not going to go there. Okay, now that makes sense because we have 1/10 of the charge, and we're starting with a time constant of 10. So in one time constant, we drop down to 36%. Okay? And in two time constants, we would drop down to 36% of 36%, which, if you think about that, is going to be a little bit more than 10% of the original. So see if that makes sense. Okay, so it makes sense that we have about 1/10 the charge after about 2 time constants. So what's the current at that point? Well, we just know that I is equal to I naught, e to the minus t over RC, and we're just going to do magnitude, okay? And we can just write this current in terms of I naught, okay? And I naught, if you recall, was equal to Q naught over RC. And then that's going to be times e to the minus 23 tenths. Okay, so Q naught is 5 microcoulombs, but the time constant is 10, so it's going to be 0.5 e to the minus 23 over 10. And we have, that's going to be microcoulombs, so whatever we're going to get for this current is going to be in terms of microamps, if I'm going to be doing my math correctly here. And it turns out that, let's just calculate this out real quick. So this actually turns out to give us 0.5 microamps times 0.1. So e to the minus 23 tenths gives us 0.1. So our current is 0.05 microamps. Okay, so our current has decreased drastically. We could also say that it's 0.1 times the initial current. That's probably a better way to say it. Okay, so that brings us to the end of our discussion of RC circuits and also to our end of direct current circuits. In our next unit, we're going to be talking about what happens when charges are in motion. So we'll be looking at magnetism. After that, we'll be moving on to sources of magnetic fields and electromagnetism. And we'll also study different types of circuits, such as the LC, the LR, and the LRC circuit, all of which are very important. So we will see you next unit.